Good day, everyone. Today, we will be discussing how to determine natural frequency for single degree of freedom torsional systems as part of the course Me22088. My name is Dr. C. Sendamrai Kandan and I am Associate Professor in the Department of Mechanical Engineering at SVC. Today, we are going to explore the concept of free vibration in an undamped and damped torsional systems. Let's start by looking at the fundamental principles that govern this type of motions. We will begin with the theory of torsion in circular shafts. From this theory, we derive a crucial relationship, that is, this equation tells us that the torque is given in the form of mt, which is required to twist a shaft, is directly proportional to shear modulus G, polar moment of inertia, and inversely proportional to the length of the shaft. Let's break down. That is, here m of t is represents the torque that causes the twist, denoted by the angle theta. G is the shear modulus, a material property that indicates its resistance to deformation by shear stress. L is simply the length of the shaft, and I suffix naught is the polar moment of inertia of the shaft cross section, which is essentially quantifies the shaft resistance to any torsional deformations. Now let's look at a visual representation. We have a shaft that is going to be length L and diameter D, which is fixed at the top. At the bottom, we are having a disc. The polar moment of inertia of the disc is J naught. When we apply a torque to this disc, the disc twists by an angle of theta. The diagram B simplifies this by showing the disc in isolation. We see the torsional stiffness, that is K suffix T. Okay, we see the torsional stiffness, that is going to be K suffix T, acting against the displacement theta. Also, we can know that is theta is displacement, angular displacement, theta dot is angular velocity, theta double dot is angular acceleration. The next step, we will use this fundamental relationship to derive the equation of motion for this torsional systems and explore its free vibration characteristics. Building on our understanding of the torque-twist relationship, we can delve into the dynamic behavior of this torsional system. Let's start by defining some key important parameters. First, we have the polar moment of inertia, denoted as I suffix naught. For a solid circular shaft, that is, I naught is given as pi d to the power 4 divided by 32, where d is the diameter of the shaft. This value represents shaft's resistance to any torsional deformation. Next, we introduced torsional spring constant, that is K. This constant represents the stiffness of the shaft in resisting the twist. We can express it as the torque divided by the twist angle, that is mt divided by theta, or it can also be represented in the form of substituting the earlier equation we seen in the first slide. That is, we can get, instead of mt, we are substituting it. So we are getting gi by L. Further, if you are substituting for I, okay, I naught, that is pi d power 4 by 34, then the equation will become like this. Let me apply Newton's second law of motion for this disk. That is, what this Newton's second law of motion is telling, that applied torque is equivalent to the restoring torque. So applied torque formula is, what is the applied torque formula? Applied torque is J naught theta double naught. Once again, reiterate that theta double naught is acceleration. Then it is equivalent opposite to the restoring torque kt theta. Since we are writing all the terms in the right hand side itself, the equation becomes j theta double naught plus kt theta equal to 0. From this equation of motion, you can further write it as theta double dot kt divided by j equal theta equal to 0. This kt, torsional stiffness divided by j, will be written as natural frequency. This frequency represents the system's inherent tendency to oscillate. It's calculated as the square root of k suffix t divided by j naught. What is k suffix t? It is torsional stiffness. J naught is going to be your polar moment of inertia. The frequency, which is the number of oscillations per second, is given by dividing omega divided by 2 pi. So we can get the frequency in terms of hertz. Similarly, the period can also be determined using the formula period equal to 2 pi f. So we can substitute f here. So remember all these parameters which relate back to our physical system, that is shaft with its dimensions, material property g, and the disk with its moment of inertia. By understanding these relationships, we can analyze and predict the vibrational behavior of undamped torsional systems. We have explored the fundamental principles of torsional vibration, but it is important to keep in mind some practical considerations and applications. Let's take a look at a few key aspects of the system. First, we need to remember that the equations we have derived assume a circular cross-section of the shaft. The shaft supporting the disc as a non-circular cross-section, we cannot directly use the standard formula for torsional spring constant. In such cases, we need to determine the appropriate torsional spring constant, that is Kt, based on the specific geometry of the shaft. This often involves more complex calculations or experimental measurements. Second, let's look at the polar moment of inertia of the disk, which is denoted as J naught. We have seen that it is crucial for determining the natural frequency of the system. For a disk, we can express it in two ways. We can calculate using the disk mass density, thickness, diameter. Otherwise, we can also use it using the weight, diameter, and oscillation due to gravity. Both forms are equivalent, and you can choose the one that most convenient based on the available information. Let's quickly define these terms. Rho represents mass density of the disk material. H represents thickness of the disk. Capital D represents diameter of the disk. Capital W represents weight of the disk. As usual, our G is acceleration due to gravity. Finally, it is worth noting that a torsional pendulum, like the one we have been discussing, has an important application in mechanical class. The precise and predictable oscillation of a torsional pendulum can be used to regulate timing mechanism in this mechanical clocks. We are now going to shift our focus from torsional systems to another type of oscillating systems, the compound pendulum. The system is a classical example how gravity can induce oscillatory motion. Imagine a rigid body like the irregular shape shown here, pivoted at a point O other than its mass center of mass. When displaced, the body will oscillate about the pivot point under the influence of its own weight. This is what we call a compound pendulum. Our goal is to determine the natural frequency of oscillation for this system. Let's analyze the forces involved. Consider a displacement of the body by an angle theta. The weight of the body denoted by W acting downwards from its center of mass G. This weight creates a restoring torque that tries to bring the body back to its equilibrium position. The magnitude of this restoring torque is given by WD sine theta, where d is the distance between pivot point O and center of mass. Applying the Newton's principle, we can able to write the equation J theta double naught, which is equivalent opposite to the restoring torque WD sine theta equal to 0. For small angular displacements, we can write it as sine theta can be changed to approximated to theta. This simplifies the equations. We can then solve for the natural frequency, which is denoted as omega n. So as usual, we can see that theta double dot plus W by J d theta equal to 0. So this term represents omega n. In summary, a compound pendulum oscillates due to the restoring torque created by its own weight acting at a distance from the pivot point. By applying the Newton's second law, making a small angular approximation, we can derive the natural frequency of oscillation. This frequency depends on the weight, distance between the pivot and the center of mass, and mass moment of inertia about the pivot point. If you have any doubt, that is how this WD sine theta comes, let I explain. That is, this is theta. If we are going to resolve this against horizontal side of this, the force acting here is W. Then this angle is going to be the opposite side of the theta. That's the way that we are getting it is WD sine theta. So the opposing force is WD sine theta. Applied force is J theta double dot. Building on our understanding with respect to the compound pendulum, let's delve into some further relationship and insights. We already derived the natural frequency, and now we will explore how it leads to simple pendulum and the concept of radius of gyration. We can compare the natural frequency of a compound pendulum to that of a simple pendulum. To do this, we have introduced the concept. The length of an equivalent simple pendulum is L. This length is defined as J suffix naught, that is the mass moment of inertia about the pivot point. M is the mass and D is the distance between pivot and center of this mass. This equation allows us to find the length of a simple pendulum that would have the same natural frequency as our compound pendulum. Very important, you have to note that this length can able to calculate the natural frequency of a simple pendulum as that of our compound pendulum. Now let's introduce the radius of gyration denoted as K naught. The radius of gyration is a measure of how the mass is distributed around a point or axis. If we replace J naught with M suffix K naught square, that is J naught is going to be replaced by mass into K naught square. That is the K naught is the radius of gyration about the pivot point O. We can rewrite this equation. If this is going to be replaced, L will be termed as M K naught square divided by M D. Hence, what will happen? We can cancel M. So L equal to K naught square divided by D. Equation shows that the square of the radius of gyration about the pivot point is equal to the square of the radius of gyration about the center of mass plus the square of the distance between them. This equation can be substituted here in equation 6.6 such a way that L can be rewritten as L equal to kg square plus d plus d square by d. So d will get cancelled. We will eventually get L equal to kg square by d plus d. We have also seen how the radius of gyration plays a crucial role in understanding the mass distribution and natural circular frequency of the compound pendulum. This relationship provides deeper understanding of the dynamics of the system. Now, let's introduce a related concept that often discussed in the context of compound pendulum, that is center of percussion. Interestingly, the center of percussion coincides at OA, where OA is the length of the equivalent simple pendulum, where L is going to be the length of the equivalent simple pendulum. This means that if you strike at point A, there will be no reactive force felt at the pivot point O. Let's see what we discussed in the last slide, that is center of percussion. Here, we have been exploring the relationship between the compound pendulum and the equivalent simple pendulum. We are going delve deeper into some geometric interpretation and further simplify our equations. As discussed earlier, k naught square equal to kg square plus d square is here. It is going to be radius of gyration about the center of mass g. Next, we are going to be see that we also derive that substituting in the length of the simple pendulum, equivalent simple pendulum, this equation we are getting L equal to kg square divided by d plus d. Hence, we can get, let me take, this is going to be the total length L. This is total length L. So what is this L? L equal to G, that is the D, okay, plus this GO. So it is only given here. So I am writing it, that is the entire length is going to be represented as L. This is D and remaining length is GE. That only written here. L equal to GA plus D, which is equivalent to the OA from the pivot point O to the point at the A point. Okay, the A point is going to be the center of percussion. This means the distance OA is equal to the length of the equivalent simple pendulum through this equation. With this geometric interpretation, if we are substituting in this equation 8, what we will get, compare these two things, L equal to GA plus D, here L equal to kg square D plus D. So hence, GA will become, GA is equal to kg square by D. Now, using this, what is GA? GA is nothing but this point. Okay, using that, you can able to get different forms of natural frequency. Already we derived natural frequency in the form of root of G divided by K naught square by D. Otherwise, it can also be root of G by L. Now, the L can also be changed to OA. This L can also be changed to OA. That is the conclusion. From this discussion, we are going to arrive that is, natural frequency can be expressed directly in terms of acceleration due to gravity and distance OA, which is the length of the equivalent simple pendulum. Center of percussion is a point on an extended rigid body impacting a pivot such that no reactive shock at this pivot point. This is under center of percussions. In simpler terms, what we can say, if you strike a compound pendulum or this hammer at this particular center of percussion, there will no be sudden jarring or force felt at the pivot point. This concept is crucial in designing the tools like bat, this bat, otherwise hammers or even doors. So there should not be any, that is, it will minimizes the impact felt by the users. We are holding here, is it not? So we have to put the hammer head here only at the center of percussion. So if the hammer is hitting the nail, then whatever the reaction we are getting in our hand is very, very less. That is the meaning. Similarly, while we are using this bat, similarly, we are using this for impact test. Impact test, if this the ball is going to be striking on the specimen, the reaction at this point will be very, very less. That is, the pivot point O is effectively the hand of the user. In this case, okay, the user feels minimum jarring in their hand, making the hammering action more efficient and comfortable. Okay, in the same case, it is going to be the, for the second case, it is a bat. Okay, A is the center of percussion. When a ball is struck on this bat, the impact force is efficiently transferred to the ball only, the minimizing the shock felt by the user who holding the bat at this point O. This image depicts a more technical application. Here, a pendulum is used to impact a specimen held in a vise. By ensuring the impact occurs at the center of percussion A, we minimize any unwanted forces or vibration at the point O. This is crucial for accurate and controlled impact testing of materials. Finally, the image D illustrates a more complex application, that is perhaps a simplified representation of a vehicle suspension system. Here, point O could represent the axle or suspension joint. A could be a point on the wheel or suspension arm. The proper design ensures the impact from road irregularities are absorbed effectively at A itself, minimizing vibrations felt by the vehicle's frame at O, providing a smoother ride. This examples demonstrates the wider range of applications of the center of percussion, whether it is simple tool like a hammer or a complex system like a vehicle suspension. Understanding and utilize the center of percussion helps us to optimize the performance, minimize the shock, and improve the overall efficiency of the systems. This principle highlights the importance of considering dynamics, impact forces, while designing the various mechanical systems. So far, we have discussed undamped torsional systems, where we assumed no energy loss due to friction or any other dissipative forces. However, in real world scenarios, damping is always present. Let's now consider a torsional system with viscous damping. We will analyze a single degree of freedom system with a viscous damper, as given in this figure. Imagine a disc with moment of inertia J0 attached to a shaft with torsional stiffness K suffix T. Now the disc is immersed in fluid that provides the viscous damping, represented by the damping coefficient C suffix T. In a diagram, you can see this physical setup clearly. The disc J0 is submerged in the fluid represented by the shaded area. The shaded area represents the fluid. Shaft K suffix T connects the disc to the fixed point. When the disc rotates, fluid resists its motions, providing the viscous damping force. This diagram simplifies this by showing the free body diagram of the disc. We see the torsional stiffness K suffix T acting as a restoring torque. We also see this viscous damping torque. Since we introduced the damping, we are having the additional torque called as viscous damping torque C suffix T, which is opposes the motion once again. Remember, theta is the angular displacement, theta dot is the angular velocity, theta double dot is angular acceleration. In this system, viscous damping force is proportional to the angular velocity theta dot. This means faster the disk rotates, greater the damping force. Damping coefficient C suffix T quantifies the strength of this damping force. In the next step, we will derive the equation of motion for this damped torsional oscillation system and explain how damping affects its behavior. We have introduced the concept of viscous damping in torsional systems. Now, let's look at this mathematical representation of this torsional system. That is, the viscous damping torque, which opposes the motion of the disk, is given by minus, that is, it is opposing C suffix T theta dot. Theta dot is velocity. T represents the damping torque. C represents the viscous damping coefficient. Okay, I can write it here. CT represents, it is viscous damping coefficient. The negative sign, indicate the damping torque. This is acting in opposite direction to the angular velocity. Now we can put together all the opposing forces. Then what will happen? We will get that applied torque J theta double dot equal to, then it is going to be the viscous damping torque, that is CT theta dot, plus that it is minus, it is opposing stiffness due to because of the shaft KT theta. All this minus will come to the next one side. We will get the equation of motion. That is, equation of motion represent the balance of all the torques acting on the disk. Okay. So now from this equation we can come to that one important thing. What are the thing is the equation of motion have mass moment of inertia, kT spring constant of the system, theta, that is angular displacement of the disk, theta dot is angular velocity of the disk, theta double dot is angular acceleration of the disk. We have established equation of motion for a torsionally damped system. Now let's explore the behavior of such a system in the underdamped case, which is characterized by oscillations that gradually decrease in amplitude over a period of time. In the underdamped scenario, the frequency of damped vibration denoted as omega suffix d is given as root of 1 minus psi square into natural frequency. This equation shows that the damped frequency is related to the undamped natural frequency. Next, we can able to see that the critical torsional damping coefficient can able to be related with respect to the damping ratio. Okay, that is the damping ratio is going to be given as Ct divided by C suffix CTC. Here it is going to be the critical torsional damping coefficient, where CTC is critical torsional damping coefficient. Okay. So now this CTC can be substituted with 2 times of J naught omega n. And similarly, if you are substituting what is going to be omega n, that is root of kt by j naught here, we can rewrite the same. That is the ratio between ct by ctc can be represented mathematically like this. That is c suffix t, just discuss damping coefficient. This is, but CTC is critical torsional damping constant, that is rewritten as 2 J naught omega n. Now once again rewritten as 2 root of k suffix t into J naught. This, all these parameters are very useful to determine what is going to be the natural frequency and how to enhance the damping capacity of the torsional systems. While completing the free vibration of torsional systems, in the next slide, I am going to see how to calculate natural frequency for this torsional system with some practical problems. Thank you.